Hello, Bulldogs. We are continuing our study of calculus. We are in Chapter 2, Limits and Rates of Change. And today we're looking at Section 2.1, the Tangent and Velocity Problem. I am in page 1 of your Chapter 2 packet, and we are just kicking off a brand new unit. So the first section of your notes talks about what is the difference between a line tangent to a circle and secant to a circle. And what you probably recall from geometry class is that a tangent line is a line that intersects a circle at exactly one point. But in reality, we're usually working with some kind of figure that is not a circle. In fact, if we graphed a circle on an xy coordinate plane, it wouldn't be a function. So we're more likely working with, let's say, something that looks like a polynomial. And if I were to eliminate this other portion of the graph, that looks like what we typically refer to as a tangent line. But we know a tangent line only intersects a circle once. Well, that is not necessarily the case when we're talking about other graphs. It still will only intersect this graph at one point in the nearby neighborhood. And so when we talk about looking for tangent lines, it's okay if this graph of that tangent line intersects somewhere else. I'm really focusing on this area right here around point P. If I were to try and sketch a tangent line over here, my tangent line would just skim the exterior of the curve. If I were to draw one right here, there's another tangent line. Here's another tangent line. Now I know that if I extend these lines, they're going to intersect again over here, but I really only care about that little neighborhood. Nice little example I like to use is if I were talking about a person standing on a mountain. I know you don't stand on a mountain quite like this, you might fall over, but that person's line of sight is going to go in the exact same direction as that tangent line. If I had a person standing right at the top of the mountain, their line of sight would be horizontal. That's exactly what that tangent line at the top would look like. So our focus today is going to be on finding equations of tangent lines. Okay, so we're going to take a look at example number 1. It says find the equation of a line tangent to the curve y equals x cubed at the point 1, 1. All right, so the first thing we know is that if I'm looking for an equation of a line, I need a point and I need slope. But if I'm only focusing on one point, if you have a tangent line that only intersects at one point, how do you find the slope with one point? You really can't. So what we're going to do is we are going to rely on observing the slope of secant lines that are close to that tangent line. And we're going to look at the closer we get to that tangent line point, that fixed point that we're focusing on, 1, 1, what is the slope of the secant line approaching? So I'm going to start by just graphing y equals x cubed. So I know that's 0, 0. We have a point at 1, 1. A point at 2, 8. So that's going to be way up here. Negative 1, negative 1, negative 2, negative 8. All right, so I'm going to sketch this thing in. And what we are looking for is we are focusing on the point 1, 1, which is right here. So I am looking for the tangent line at that point. Now I'm just going to kind of draw one in here, but it might not be super accurate. I don't have the most accurate graph drawn here. But that pink line is really what I'm trying to find the equation for. And I know a point, but I need to find slope. So I'm going to start by finding the slope of the secant lines as we get closer and closer to that point. So a good starting point, I'm going to come over here. We're going to use this little table to keep our data organized. And the first thing I want to do is I want to find, well, I have the coordinates 1, 1. I'm going to leave that in for my top row. But I'm going to pick another point near 1, 1. And since I already have this point out here at 2, I'm going to go ahead and list the point 2, 8. And I want to find the slope between 1, 1 and 2, 8. Now that is what we call a slope of a secant line. A secant line intersects a graph at 2 points. Now we know that green line is nothing like the pink line, but this is just kind of a starting point for us. So over here in this third column, I'm going to find the slope between these 2 points. I'm going to find my change in y over my change in x. So my change in y would be 8 minus 1. Change in x would be 2 minus 1. So 7 over 1, which is 7. So the slope of that very first secant line is going to be 7. All right, we want to pick something a little bit closer to the point 1, 1. So instead, I'm going to go with maybe 1.5. So 1.5 would be, I don't know, somewhere in here. We're going to find exactly where it is. So 1.5 is like 3/2, but we are definitely going to use our calculator today because we're going to be looking at some crazy decimals. So I am going to go to my y equals screen. Let's clear anything else out that we have in there. If your plots at the top are highlighted like that, you want to unhighlight those. And I'm going to drop in my x cubed function. And you can look at the graph of it if you want. I'm just going to go to a table. And in this class, we are more than often, we're going to want to be able to input our own values in this table. Like for right now, I can type in the number 2 and it gives me an answer. You might not have that setting on your calculator, so let's go ahead and check our table settings. So second window, and you want your independent variable to have ask highlighted. That will allow us to input our own independent variable, which is x. All right, now I'm going to go back to my table, and I'm going to start with 1, and I'm going to plug 1 in. Actually, I'll put that up at the top. And then I plugged 2 in next. Now I want to find my value when I substitute 1.5 in. So we get 3.375. You are certainly welcome to leave these as fractions if you want, but I warn you the numbers are going to get a little ugly soon. So I now want to find the slope between 1.5 3.375, which is somewhere right in here. And the slope between that point and my fixed point. My fixed point is always that 1, 1 point. You can see my green line was very different from my pink line. My purple line is still different from the pink, but it's closer. So the slope of the purple line is getting closer to the slope of the pink line. So I'm going to find my slope here. So I'm going to subtract y minus y over x minus x. So that's going to be 3.375 minus 1 over 1.5 minus 1. And we can absolutely use our calculator to do that. And we get 4.75 for my slope. All right, I need to get a little bit closer. So instead of 1.5, what's a number that's closer to 1 than 1.5? Well, I'm going to go a little bit more extreme here. I'm going to choose 1.1. And 1.1 is going to be super close to that fixed point 1, 1. In fact, when I draw my tangent line in here, it's really starting to look like the pink line. And I'm going to find my slope. Now, I'm getting a little sick of calculating the slope by hand. So I'm going to have the calculator calculate slope for me. So in this class, we're always shooting for ways to work smarter, not harder. So I'm going to come down here, and I know that when I'm calculating the slope, I always have one fixed point. That fixed point that never changes is 1, 1. So I'm finding the slope with the point 1, 1. My other point does change. I started with 2 for x, 1.5 for x, 1.1 for x. So what I'm going to do is I'm going to leave this as a variable x. So if my input was x, what would my output be? Well, my output would be x cubed, which is y. And now, to calculate slope, I'm going to find the slope between these 2 points, which in this case includes an expression. So we would have y minus y, x cubed minus 1, over x minus 1. And what I'm going to choose to do on my calculator is right now I have y1 as my first column in my table, or my first equation on my y equals screen. I am going to make this third column in my table be y2. So I'm going to go back to my calculator, and I already had x cubed here. Now I am going to, in place of y2, I am going to have the calculator make slope for me. So I want to put a fraction in here. So there's a secret hidden menu. If you hit alpha y equals, number 1 is numerator over denominator. Let me speak that over. We're getting a little bit of a glare here. And I'm going to choose option number 1. And I'm going to type in x cubed. Make sure you hit your right arrow to get out of the exponent. Minus 1 over x minus 1. And now, if I go back to my table, you can see from the very beginning, obviously I got an error on the first one because it's using 1, 1 as a point. You can't find the slope between 1, 1 and 1, 1. You get 0 over 0. So that's why we have an error. But 2, 8, I have the slope of 7, so that confirms what we had over here. I'll look at the next line down. 1.5, my slope was 19/4. Oh, if you do not want your calculator to be calculating a fraction like that, we can change the mode of our calculator so that it only spits out decimals to us. So let's go to mode, and I'm going to go down to answers. And right now it's on auto. I'm going to change that to decimal. And now when I go to my table, there we go. Now we're looking at decimals. All right, so what are we doing? We just found the slope at 1.5, which is 4.75. Now I'm going to type in my next point that I was working with, which is 1.1. And my x value is 1.331. And my slope is 3.31. That was a lot faster than calculating that slope by hand. All right, let me see if I can find one more color here. Let's go with red. So I want to get even closer to 1 than 1.1. So I'm going to go with 1.01. And 1.01 is so darn close that you can't even see it. I've got too many pen colors in here. But 1.01 is very close to 1.1. In fact, so close that its tangent line starts to look just like the pink one that we started with. So I'm going to go back to my calculator. Let's get rid of that glare. And I'm going to type in 1.01. And we've got 1.0303 for my y value. But more importantly, what we want to grab is the slope. And I have 3.0301. And I'm going to get even closer than 1.01. So I'm going to go to 1.001. And below that, 1.0001. So 1.001, 1.001. The closer and closer we get to 1, the more that our secant line looks like the tangent line. And so look at your slope at 1.001. It is 3.003. And at 1.0001, it's 3.0003. So now what we want to look at for is what trend are we seeing happen with our slopes. You can look at your table on your calculator or on paper. The closer that I get to the x value of 1, the closer my slope is getting to what looks like 3. So part A says, what is the slope of the secant lines approaching? It looks like the slope of the secant lines is approaching 3. Okay, so now we want to find the equation of the tangent line. Well, the slope that the secant lines are approaching is what we are going to assume the slope of the tangent line is. Now we're doing this using an approximating method right now. Later on in the course, we will learn how to do this algebraically. So I know my slope is 3, and we are also using that fixed point that we started with, 1.1, excuse me. And I'm going to use point slope form. So y minus 1 equals 3 times x minus 1. And I'm absolutely fine with you keeping your equation in this form, but if you wanted to compare it to what we have graphed on here, y minus 1 would distribute, get slope-intercept form, equals 3x minus 3, y equals 3x minus 2. Now you can see my graph was not accurate to begin with because my pink line does not look like it intersects down here at -2, but this thing is actually a lot steeper and it crosses down here, and the slope of that pink line that I started with is 3. Okay, so we are practicing the approximating method of finding the limit of slope. So let's take a look at an application of this. So suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto. In case you don't know what that looks like, Toronto is a beautiful city if you haven't been there, and that is CN Tower. There's actually a really cool rotating restaurant at the top and a glass bottom floor you can stand on. I had the chance to go there a number of years ago. And so the story says we are dropping a ball from the upper observation deck. Don't do that. That would be very illegal. 450 meters above the ground. Find the velocity of the ball after 5 seconds. Okay, so how are we now talking about velocity? Well, there's kind of a little blurb here. And let me see if I can get you a little bit closer. So what this little blurb says, see if we can focus a little bit better. There we go, that's good. Through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. So, and this is neglecting air resistance. For my physics and science experts out there, we are ignoring air resistance right now. If the distance fallen after t seconds is denoted by s of t, so oftentimes we'll use that for distance or for position, and it's measured in meters, then the equation that he created is s of t equals 4.9 t squared. So this is the equation for meters. There is a different equation for feet. So the challenge is we are trying to find velocity. Well, something that we will often refer to in here is average velocity as compared to instantaneous velocity. And so the next part says the difficulty in finding the velocity after 5 seconds is we're dealing with a single instant of time. So and we're looking for slope of lines. So how is it that I'm going to find the slope at a single instant of time? Well, we really can't find it at a single instant of time, but we're going to look for very close intervals. So the fixed point we're focusing on is 5, and then they want us to start by looking at the average velocity from time equals 5 to time equals 5.1. So I'm going to come up here, we're going to use this table, and again we're going to have x, we're going to have y, we're going to have slope here. And our very first point, our fixed point is going to be 5. So the first thing we're going to do, we're going to go back to our calculator, go to y equals, we're going to clear out what we have in there, and we're going to drop in that equation, 4.9. It's t squared, but we're going to drop in x squared. And I'm going to go to my table, and let's drop in 5 and find out after 5 seconds, my position is 122.5. So that is going to be my fixed point. So the next question that they ask us to find is, what is the average velocity from time equals 5 to time equals 5.1? So when we talk about looking at the difference between 5 and 5.1, I'm going to be looking for the slope between those. So this x value that we're looking at next is going to be 5.1. If you're thinking graphically what this thing looks like, if I were to draw a tiny little graph in here, this is a parabola. And when we talk about a parabola, usually we have some behavior on this side. But Galileo is dropping, or someone is dropping the ball, and this is traveling. So this value, if we think of x and y, x is our time, and the y value is the distance traveled. Not height, but distance traveled. So we would expect that distance traveled to increase, get higher and higher and higher. So the reason why we are looking for slope here is anytime I look for 2 points, so let's say that's 5, and there's another point here. If I'm looking for the slope between those 2 points, my vertical distance is going to be a distance, which would be in meters. My horizontal distance, which would be time, is in seconds. So the slope represents meters per second, which is a velocity measurement. That's why when they ask for velocity, we are looking for the slope. Okay, so we want to find the slope between 5 seconds and 5.1 seconds. So if you wanted to manually calculate the slope, you certainly can. But I know that I'm going to try to work smarter instead of harder. So I'm going to come down here and I'm actually going to make a formula again for slope. So we have this fixed point, 122.5. My other point is going to be a variable point. It's going to change. So we have x, and then for my y coordinate, it's going to be if I plugged in x, I would have 4.9 x squared. So when I calculate my slope, I'm going to look for my change in y's. 4.9x squared minus 122.5 over x minus 5. And that is the formula I'm going to be putting into my calculator that I'm going to call y2. And I put my original function in here for y1. So let's come back to my calculator. Go to my y equals screen. We've got my 4.9x squared. I'm going to go down to y2. I'm going to grab that secret little menu. So alpha y equals, that gets me my fraction line. So I have 4.9x squared minus 122.5. And on the bottom, we have x minus 5. Okay, so now when I go to my table, the y1 column is going to be my y values. At each of the x values I choose, my y2 column is going to be the slope. So what we're looking for here, I'm going to go back to my table. I am looking for, scoot this over here, my slope between 5 and 5.1. So my y value at 5.1 is 127.45. If I manually calculated the slope, 127.45 minus 122.5 over 5.1 minus 5, I would get 49.49. Now that was between these 2 points, time equals 5 and time equals 5.1. What if I wanted to get even closer than 5.1? How about 5.01? Now, I don't really care about the y values. I made a column, but I really don't need those. I'm not using those for anything. I'm going to hop over to my y2 column and grab my slope, 49.049. I'm starting to see a little trend here. Let's get a little bit closer. Let's go 5.001. 49.005. We can try one more time, 5.0001. And now it says 49, but just so you guys know, if I were to move my cursor on top of that, it's not exactly 49. There is going to be some slight difference way far out. It's just such a small value that when the calculator rounds it, it's rounding to 40.49. But it's really going to be 49.00049. So we have found that the average velocity, so that was our question, find the average velocity from t equals 5 seconds to 5.1 seconds, so a very short time interval. We found that slope to be 49.49. So in terms of the slope of that secant line, it was 49.49. If I want to put a unit on there, we know that that is meters per second. That's from the graph that we created earlier. That's how we generated that slope. But to find the instantaneous velocity, that's different. Average velocity is a slope of secant lines, so slope between 2 points on a line. Instantaneous velocity is what we will refer to as the slope of the tangent line. And just like on the previous example, we can't find the slope of a tangent line from one point, so what we look at is what is the secant line slope approaching the closer our value gets to 5. And it definitely looks like our slope is approaching 49. So as x approach, whoops, let me scoot this up. As x approaches as x approaches 5, let's get rid of that. So as my time value is approaching 5 seconds, our instantaneous velocity, which is like our slope, is approaching 49 meters per second. And they are not asking you to write an equation, they're just asking you to find what the velocity of the ball was after 5 seconds. So we were looking for the instantaneous velocity. Okay, this other set of data over here, I just wanted to clarify, I don't like having incorrect information on my notes. This is an old picture from our textbook, and our textbook is rather old. And the caption states that the CN Tower is the tallest freestanding building in the world. That is no longer the case. Lots more buildings have been created since then. So the tallest freestanding structure is actually a structure in Dubai. You can see CN Tower still made the list. Right after that is the One World Trade Center. Okay. So there are a couple more examples in your notes. I'm just going to make a couple comments here. We're not going to do these questions all the way through. But what's different on example 3 is instead of us being given an equation, we are being given a table of values. So this table holds 1,000 gallons of water, and the water is draining. The values in the table show the volume of water remaining in the tank after T minutes. So you can see the volume is getting smaller and smaller as time has gone by. P is the point 15,250. That's going to be our fixed point that we're using, 15,250. And it says find the slopes of the secant lines PQ when Q is the point on the graph when T equals 5, 10, 20, 25, 30. So let's say we were going to look at time being 5. Well, instead of us having to plug 5 into an equation, we actually have that data on here. So that would be the point 5, 694. And so what they're looking for is for us to find the slope between time equals 5 and time equals 15, since the 15 is our fixed point. That's what they're calling P, and they are changing the values of Q. So we would have 694 minus 250 over 5 minus 15. And obviously, definitely use your calculator for that. I'm going to go to my home screen, clear that out. Alpha y equals, so I can get a fraction, 694 minus 250 over 5 minus 15. So we get a slope of negative 44.4. Let's put a unit on there. So this is change in y over change in x. So change in y would be gallons over change in x would be minutes. So this is the rate of change that our volume is changing. So that would be the rate of change of gallons per minute. So it is dropping 44.4 gallons per minute. They are asking you to find other values. So let's say I tried 10 next. For time equals 10, we would have the point 10, 444, and we would be finding the slope between time equals 10 and time equals 15. So 444 minus 250 over 10 minus 15. And we get negative 38.8. I'm going to do one more on here, and I'll let you do the rest. But I'm going to do that time equals 20. So 20, 111 is our point. So our slope would be 111 minus 250 over 20 minus 15. And we get negative 27.8. So the reason why I wanted to show a few examples here is B says estimate the slope of the tangent line at P by averaging the slopes of two secant lines. So I'm looking for the instantaneous rate of change of my volume in my tank. So if I want to average slopes of two secant lines, which secant line should I choose? I would choose the secant line between 10 and 15 and between 15 and 20. So those are the two that are closest to 15. So at time equals 10, my slope was negative 38.8. I'm going to use this one. And at time equals 20, it was negative 27.8. So they're asking me to average the average rates of change. So average those two. And that is an old school average. So negative 38.8 plus negative 27.8 divided by 2. And so we get negative 33.3 gallons per minute. Okay, part D says, what does the slope represent? Well, we kind of already talked about that, but it's also written on here. It represents the rate at which the water is flowing from the tank. Write the equation of the line tangent to the curve at point P. We're going to use this new slope right here, negative 33.3, for our rate of change at point P. And we have point P right here, 15,250. So we would have y minus 250 equals negative 33.3 times x minus 15. And I'm just going to leave it in that point slope form. Okay, I'm going to skip over 4, but for example 4, it is very similar to the very first example that we did. Our fixed point is going to be 5,3, and they're having you look at and observe the slope as you get closer and closer to 5. So you can get closer and closer from one side, 4.5, 4.9, 4.99, 4.999, or you can come from the other way. So 5.5, 5.1, 5.01, 5.001. And you'll see that on either side of 5, these are going to be approaching the same exact number. All right, I want to give you one last hint, and this is really a hint for your homework. So for example number 5 on your homework, you're given time increments, such as 0.5 seconds. And so when you are looking for time increments, and they ask you to start at time equals 2, if they tell you the time increment is 0.5, that means your next time value is 2.5, meaning the first x value that you're using is 2, find your y value. The second x value is 0.5 seconds later, which is 2.5. And then you would find the slope between those 2 points. On number 7, they ask the question slightly differently. It says when provided intervals such as 1 to 2, so this interval, that is an x value, and that's another x value. They're giving you a start of an interval and an end of an interval. So they're saying for your 2 points that you need in order to find your slope, your very first point is going to be a time value of 1, and then your second point is going to be a time value of 2. So that's just 2 different ways they're telling you exactly what kind of points they want you to use to find your slope. One is telling you the time increment, the other is telling you the time interval. Okay, so I hope that was helpful. We are, again, reviewing approximating slopes and approximating tangent lines today. Thank you so much for listening. Good luck.